Okay, having discussed the equality constraint and the conditions for our optimum solution under the equality constraints, let us move into the inequality constraint. So, we consider a single inequality constraint of the form C of x is greater than or equal to 0. Now, if we choose a direction d around the point x, C of x plus d is strictly greater than or equal to 0, or 0 is less than or equal to C of x plus d. You have to notice the change in the inequality that is appearing here against the strict equality constraint that we had when we looked at just a perturbation around x, right, a direction which just perturbs around x. Now, as usual, I expand through Taylor series approximation. C of x plus d is approximately C of x plus del C transposed d, right. This is what I have. Now, C of x plus d is strictly greater than or equal to 0. Therefore, C of x plus del C dot the direction is strictly greater than or equal to 0, because Cx is also greater than or equal to 0, right. We plug in this condition here. So, therefore, Cx plus del C transpose d is greater than or equal to 0, because this is greater than or equal to 0 and this is also greater than or equal to 0. So, I call this inequality to be C. Considering the example from the circular constraints, the inequality conditions can imply that we are optimizing over points that are lying inside or outside the circle, right. So, I mean, if I am looking at always a quantity which is Ci is, if I look at x square, x1 square plus x2 square is less than or equal to a square, then this is an inequality constraint that is satisfying all points that are lying inside the circle. And if I negate the sign, right, I put minus x1 square plus x2 square. So, this is greater than or equal to minus a square, and I transpose it, I can have a square minus of x1 square minus x2 square is greater than or equal to 0, and I can still think about my constraint in the form Cx is greater than or equal to 0, because I flipped the sign. So, a square minus x1 square minus x2 square greater than or equal to 0 still represents my constraint where I am looking at optimizing points that are lying inside the circle and also on the circle. The equality is on the circle and the inequality is inside the circle, right. So, this is an idea how we can start. Okay. Now, we have two cases here. Case A, the strict inequality holds, that is Cx is strictly greater than 0, and the other condition where Cx is equal to 0, right. So, I just want you to be careful here. So, do not always think that when Cx is greater than 0 it is always a curve. For example, in this case if Cx is greater than 0, do not imagine that it is always points that are lying outside the circle. It is not necessarily the case, because if I flip the sign here I will end up with this equation where still I have a constraint Cx which is given by a square minus x1 square minus x2 square, and Cx is greater than or equal to 0 implies that we are looking at points that are on and inside this circle, right. This is to be made very clear. Okay. Now coming back here, whenever del f is not equal to 0, that is when we have not yet reached the optimum point. So, what we have are two inequalities. Del f transpose D is less than 0, that is our condition B, right, because we do the same Taylor series expansion and then we infer this. But from what we derived just earlier, because C of x plus D is greater than or equal to 0, expanding that out, we have C of x plus del C transposed D is greater than or equal to 0. But you have to bear in mind, in the equality constraint C of x was 0, therefore, this dot I could strictly infer an inequality there, right, an equality there, that is del C dot D was strictly 0 for me. In this case it is not. Okay. So, C of x plus del C transpose D is strictly greater than or equal to 0 for inequality constraint, and you have to bear this, you have to notice this, observe this change, right. There in the equality constraint it was an orthogonality condition, that is del C transposed D was equal to 0. Here we have an inequality constraint, that is C of x plus del C transposed D is greater than or equal to 0. Okay. Now, we group these two inequalities here and call this equation set or inequality set to be numbered 2, right. Now, like the way we proceeded, a direction D that satisfies these constraints is given by D which is equal to minus C of x times del f of x upon norm del f times norm del C, and I call this equation D. We need to verify that this is holding true. Now, let us verify that equation D, which gives me the feasible direction D, satisfies the constraints given in the inequality set number 2. Okay. Now, so what I have to do is I take del f times D, that is the first constraint that I have. So, now I plug this D here. So, what I get is it is minus gradient of f times C of x, this is a scalar, times del f upon norm del f and norm del f times norm del C in the denominator. So, the Cx is a scalar, I pull this out with a negative sign. So, I land up with del f transposed times del f upon norm del f times norm del C, right. So, the first part right. This evaluates to norm del f, right. It is basically in the numerator you have norm del f square upon norm del f. So, this evaluates to norm del f. Now, these norms, so in the numerator I have so basically if I simplify this I have minus c of x times norm del f upon norm del c. Norms are greater than or equal to 0 because they measure in some sense this distance. So, it is greater than or equal to 0, positive distance. C of x is greater than 0, right, and basically you have a negative sign sticking out here. All of the other quantities are all positive, that is norm del f and norm del c, that ratio is positive, c is positive. So, you have a negative sign sticking to two positive products here. So, therefore, the first constraint is satisfied because del f times d is strictly less than 0, right. This is what we have. Of course, you have to bear in mind that in the denominator the or in the numerator the del f and del c they are non-zero quantities. Okay. Now, let us look into the second condition, which is c of x plus del c transpose d. Now, this is given by, so I need to have a underscore here because they are vectors. Now, this is c of x plus del c transposed, I plug in d here, which is minus c of x del f upon norm del f times norm del c. So, the c of x is a scalar which is outside, and this is greater than or equal to 0, right, and I have this quantity which is del c transposed del f upon norm del f times norm del c, and this quantity is strictly less than 1 unless del f is equal to del c, right, otherwise it is strictly less than 1. So, how do we ensure? You can check this out again through the Cauchy-Schwarz. Now, del c transposed del f is less than, strictly less than norm del f times norm del c, because I remove this equality condition because I do not consider the case when del f is equal to lambda del c. So, therefore, I ignore that condition. So, what we have here is this whole quantity in that I have circled out in red evaluates to some alpha which can be positive or negative, right, and a quantity which is in absolute sense is less than 1. So, absolute of that mod of this is strictly less than 1, and what I have here is it is c of x minus c of x times alpha, where alpha can be positive or negative, but the absolute value is less than 1. So, we simplify this as c of x times 1 minus alpha. So, when alpha is on the positive side, anyway this quantity 1 minus alpha is positive. So, therefore, this inequality holds. When alpha is negative, 1 minus of alpha is again positive. So, therefore, c of x times 1 minus alpha is positive and it is greater than or equal to 0, right. The only condition is when alpha equals 1, that is the case where you will have to worry about when del f equals lambda del c, that is ruled out for us. So given that, we can say that it is strictly greater than or equal to 0, right. So the equality, I just have to mark a note here, the equality is only over the case when alpha equals 1. When alpha equals 1, this quantity evaluates to 0. Okay. Now we have the other case. So therefore the solution D that I had satisfies those constraints. Now we consider the case when x is on the boundary of the constraint equation. So the case A was when x was inside the curve, right. So do not get carried away by C of x is greater than or equal to 0 or less than or equal to 0. So you can always negate the sign and arrive at the constraint, but since we are looking at the geometry of the problem where we are looking at feasible points inside the circle or on the boundary, the first case, case A, was a situation where it was inside the circle, here it is on the boundary, that is satisfying Cx equals 0. So we have two equations here, two inequalities here. The first is straightforward, del f transpose D is less than 0, that is coming from equation B that we have carried forward. The second, I had C of x plus, if you recall, C of x plus del C transpose D is greater than or equal to 0, that is the condition that I had. But since it is on the boundary Cx equal to 0 because of the boundary situation. So therefore that C of x is 0, I will end up with del C transposed D is greater than or equal to 0. Now what is important here is to visualize where the feasible solution lies. So this is important from geometric perspective, from a geometric perspective. So let us group these two constraints as number them as 3. Now del f transpose D is less than 0 is this open half space, that is I put this dotted line which indicates del f dot D equal to 0, that is the equation of my hyperplane, and everything which is lying below this curve, below this line, I just indicate this in blue shade, that is my region. Now it is not lying on this dotted line, but strictly lying below this dotted line, that is why it is an open half plane. Similarly, when I look at del C transposed D is greater than or equal to 0, I am looking into this red region here, this shaded red region where it is lying on in the shaded red region, right. That is the second part of this this equation set 3, right. This is my 3 dot A and this is like my 3 dot B, right. 3 dot B is basically this red region, 3 dot A represents this blue shaded region. So the region where these constraints are met is this overlapped shaded region that comprises of blue and red, right. That is the geometric feel of this problem. So, if I have a non-null region, then I have a solution. If it is not, then I do not have a solution. Okay. Now, when del f equals lambda del c and del f and del c point in the same direction, this is very important. That means del f is pointing like this, del c, assume this is parallel. So, this is del f, this is del c, and they are pointing in the same direction. So, as long as del f and del c point in the same direction, the regions from 3 do not intersect. So, can you see how this happens? Because I do not need, if I look at these equations these inequalities in 3, right. So, I have del f dot d is less than 0, sorry, del f, then I have del c dot d is greater than or equal to 0, and this del c can be written as 1 over lambda del f. So, the lambda anyway can be pulled out, it is 0 upon lambda, which is 0. So, it basically translates using 1 del f. I can compute, I can say del f transpose d is less than 0, other condition is del f transpose d is greater than or equal to 0, and that makes no sense because that says that they are not intersecting, right. So, therefore, the regions do not intersect when del f and del c are pointing in the same direction. So, let us look into the other case. When del f equals minus lambda del c, that is they are pointing in opposite directions. So, I think this cone will help you visualize. So, the first constraint tells me that del f dot d is less than 0. The other condition is a flip of the inequality, which again says del del f dot d is less than or equal to 0 by folding this lambda out there. So, basically when del f and del c are in opposite directions, the constraint regions completely overlap to form the half plane. It is like you rotate this plane del c transpose d greater than or equal to 0, just aligned with the plane of the that is what it means. So, in one case when they are pointing the same direction, they do not intersect, and in the other case when they are pointing in opposite directions, so they overlap to the entire half space, and we choose the same lambda which is greater than 0, so that we are consistent with how we write. So, in one case there is full intersection, right, when del f and del c are in opposite directions, and in the other case there is no intersection. Now, what is the consequence of this in terms of the Lagrangian? This is important for us. Now, let us formulate L to be f minus lambda c. So, some lambda is greater than 0, because if lambda is equal to 0, then we have no constraint, sort of. Now, del L, I mean I take the gradient on L, it is del f minus lambda del c, which is equal to 0. That is how I need to compute for my saddle point. Let us assume that I have a negative sign sticking here. Then del f equals plus lambda del c, right, because I just equate del L to be 0 and I will end up with del f to be equal to lambda del c. But from our discussion, when del f and del c are pointing in the same direction, there is no intersection, therefore, the search should stop, because the constraints, it is not satisfying this. We need to stop the solution, we need to stop at that step, because there is no search here, because the constraints are not satisfied. So, therefore, while formulating the Lagrangian with inequality constraints, we need to put a negative sign before the constraint scaled by some Lagrange multiplier lambda, which is basically greater than or equal to 0 or greater than 0. Okay. So, this is very important, this sign is very important, because if this is not, then your whole your search is meaningless when you throw this sign away. This is a very important detail, often taken for granted. So, if you have done an optimization course, you will see that these have to be carefully taken into account. But if you have not seen this from optimization courses, you will wonder whether I have to put a plus or a minus, and that makes a big difference here, because if you put a plus, which means that you are again searching because you are again in the half plane, and you know you are it is basically making no sense. Okay. So, I mentioned to you that earlier that you know a constraint with an inequality with c of x is less than or equal to 0 can be transformed into some g of x which is greater than or equal to 0 by negating the sign over c of x, right, and then the analysis still perfectly holds true. So, whether the inequality constraint is less than or equal to 0 or greater than or equal to 0, you can still formulate the appropriate Lagrangian by transforming it into the case for inequality c of x is greater than or equal to 0, and then put a negative sign to the Lagrangian and then proceed with the analysis, right. So, this is a very important detail. Hopefully, with this when we study support vector machines under various equality and inequality constraints, we can see the importance of this result in that formulation.